Hi, this third video about Chapter 14 lab work is one in which we are going to look at an example of when paired differences in data sets exist. So this particular problem that you see here is about a supermarket chain that wants to know if their buy one, get one free campaign increases customer traffic enough to justify the campaign. So for each of 10 stores, they select 2 days at random to run the test. So you have 10 stores, and on one day, they do a buy one, get one free, and on another day, they don't do the buy one, get one free. So you get to compare with buy one, get one free versus without buy one, get one free on a store-by-store basis for 10 stores. And what they want to test is the hypothesis that there's no average difference between the foot traffic in the stores as a result of this buy one, get one free campaign. So the data will look like a 2 by 10, 10 numbers measuring the number of customers who visit the stores 1 through 10 when the program is in place versus when the program is not in place. Okay, so the first thing I'm going to do is note that yes, the data are paired because each of the samples includes the number of customers at each store taken twice, once with the program and once without the program. And then the first thing you want to know is to calculate the mean difference. So in order to do that, you open the data in STATCRUNCH. And we're going to compute. The first thing is we're going to go to data. We're going to compute an expression. And the way we build this expression is we're going to take with the program and we're going to subtract the number of customers without the program. And we're going to call this computation D. So D is the difference in customers with and without the program. So as you can see, in some cases without the program, the attendance is higher. In other cases, it's lower. And then in order to compute some of the statistics involved in this process, we're going to go back to testing. Again, how did I get this D column here? This D column is data, compute, expression, and you take the variable called with program minus without the program, and the column is labeled D, and compute. And that's how we got the differences day by day. Sorry for not having focused on this earlier. Now, in order to calculate the statistics involved in either confidence interval estimation or hypothesis test for this particular situation, we're going to go to t-stats one sample with data. And the sample is going to be the data on the column called D. And we can test a hypothesis that there's no difference versus that there is a difference. Or we can build a confidence interval that the average number of days of difference between frequency of customer visits to the store with program versus without program. I decide to run a hypothesis test. I notice that the sample average difference is minus 1.1. So I go back to the problem and put the answer, check it. Then the standard deviation of the differences, which is not listed in the hypothesis tests, but can be computed by going like you did in chapter 3, summary stats columns, and do a standard deviation of the D column. And that's a 5.5 difference in standard deviation of the differences. With a standard error, for the difference, for the average difference that is calculated by the test data. The standard error is 1.74 customers in average difference from the average across all 10 stores. So that's a 1.74 standard error around a mean of minus 1.1. And then the test statistic for the null hypothesis that the average difference is 0 is also again from the same data that came from the test procedure that we calculated in StatCrunch. And this is a minus 0.63 difference, meaning that there isn't even one standard deviation's worth of a difference between the number 0 and the number minus 1.1. So there's very little difference from 0. In this case, the number of degrees of freedom is the 10 stores minus the 1 degree of freedom lost in the computation of the standard deviation and the standard error. So it's a 9 degree of freedom problem. This is a two-tail test statistic because you want to test that there is no difference in traffic against the alternative, that the program increases the mean traffic. So it's actually about increasing mean traffic. And increasing mean traffic would be a one-sided hypothesis, sorry. And it's about how the traffic increased versus the traffic is 0. And last but not least, I have to go back to checking for the p-value in the correct manner. Because in here, I tested the null hypothesis of 0 versus the two-tail version, where it could be, we could reject the null because the test is either on the greater than or the less than side. What we actually want to do is change this last part of the hypothesis test to say that we're testing equal 0 versus greater than 0 versus an increase in activity as a result of the buy one, get one free. And in this case, the p-value is 0.7284, meaning there's more than 72% chance, there's almost a 73% chance that the average difference between buy one, get one free and not buy one, get one free is really minimal or non-existent. So at a 5% level of significance, we don't reject the null, and there is not enough evidence to conclude that there is an increase in traffic due to the buy one, get one free. So the result would be that if this were a real test in a real environment, and this were, say, a Whole Foods or some sort of grocery store or grocery outlet or whatnot, the grocery outlet would be wasting money offering buy one, get one free. You shouldn't have a campaign that is ineffective. So that's what this test result reveals in this particular situation. I hope this was interesting, if not useful, and clear, if not practical. And stay tuned for more videos on how to use StatCrunch to calculate the different kinds of hypotheses and confidence intervals presented in this chapter. Thank you for watching.